So today we'll be going over the how to solve for the centroid of an area. Now this area could be in reference to any particular object or structure such as a beam. Now as an example, let's say we have the cross section of a rectangular beam in this case such as this. Now let's go ahead and give it the x and the y axis. Now one thing to keep in mind in the past, whenever I have analyzed any problems such as doing analysis on a box with a weight W, for instance, I always mention that we applied it to the center of mass, to the center of gravity of that object. Now, similarly, when it comes to the centroid of an area, as long as the material, in this case this beam, as long as the material is uniform throughout the structure, the center of gravity is going to be equivalent to the centroid of an area, right? So when it comes to area, it has to do particularly with the geometry of any part or structure. When it comes to the center of gravity, it has to do with the material itself. Now, assuming the material is uniform throughout, that means the center of gravity is going to be equivalent to the centroid of an area. So that's why it's very useful to know how to find the centroids. So in this case, we have the x and y axis. Now the centroid, the center of this area with respect to the x-axis is going to be at this point, and then we're also going to have it with respect to the y-axis. So knowing the x and the y, we'll be able to determine exactly where the center of this area is, such that we'll know where to apply the weight of any particular object to simplify our calculations and so forth. So when it comes to the equations to solving for the centroid of an area, we have it with respect to the x-axis and with respect to the y-axis. So there are two equations to remember. So to find the center of the area with respect to the x-axis, we'll be calling it x bar here, and with respect to the y, we'll call it y bar. So to solve for the centroid with respect to the x-axis is equal to the integral with respect to the area x dA divided by the integral of dA, and similarly with respect to the y. And so these are the two equations we're going to be utilizing to find the centroids of an area. So let's go ahead and do an example so the concept could be easier to understand. So for this example, we have the problem statement is locate the centroid x bar of the parabolic area. So we have this parabolic area within this region, and we have the equation y is equal to h divided by x a squared times x squared, and we have the dimensions a for the x-axis and the dimension h for the y-axis. Now let's go back to the equation of the centroid with respect to the x-axis. So we have the x bar is equal to the integral of x bar dA divided by the integral with respect to dA. So now this is where we actually, since we're integrating, we're assuming we're splitting this area up into an infinite amount of smaller areas, for instance. So after choosing an arbitrarily small portion of this area, we have this rectangle here. Just imagine this being infinitely small. The closer you zoom in, the more this will become a actual rectangle. So we have the height of this rectangle, which is h take away y, and we have the width of this being dx. Now this x bar is equivalent to the x, so it'll be the centroid of this arbitrarily small area that we just chose, some small element of that area being x. Now the area of a rectangle is equal to a length times width, so it's going to be the h take away y times x. Now, if you want to do the dA, the derivative of that area, it'll be h take away y times dx here. So this is actually your dA that you're going to be using to integrate to find that x bar. So let's go ahead and actually use the formula now. So the integral of x times dA, which is h take away y dx. But keep in mind, we also have the y function here with respect to x, so we just plug it in for y here. Let's go ahead and finish writing this up. H take away y dx. So now let's go ahead and plug in for y and simplify the integrals here. So we have the integral from 0 to a, and after distributing the x and plugging for y, we have x times h, take away h divided by a squared times x cubed dx, and the denominator here is the integral from 0 to a, h take away h divided by a squared times x squared dx. Now let's go ahead and integrate and simplify this further. So we have the integral, which is h over 2 x squared, take away h divided by 4a squared, x to the power 4 from 0 to a. Then the denominator is h times x, take away h divided by 3a squared times x cubed from 0 to a. And let's keep on simplifying this. So we have h divided by 2a squared, take away h divided by 4a squared times a to the power 4. So we see that a squared cancels and we're left with a squared here. Now for the denominator, we have h times a, take away h divided by 3a squared times a cubed. So this cancels and we're left with 1a. Now we could keep on simplifying this until we finally get our answer. So we finally have x bar is equal to 3/8 a. So this is where, with respect to the x location, the centroid of the area is located. Now you can actually do the same problem, but do it find the y bar. So you could actually define the center of the area, the centroid of the area. You'll have both your x and y location. So now solving for the centroid with respect to the y-axis or y bar, we have this formula. Now let's go ahead and draw the area, the differential area of an element. So now we see for this element that's infinitesimally small, you could actually approximate this to a rectangle, right? So we have the length being x, and we have the width being the differential dy. So the area, if we would just go with the length times width, would be x y dA. In this case, is with respect to the y-axis, so it's x dy in this case. And so this is what we're going to be using for the integrals. And since we're given the equation y is equal to h divided by a squared times x squared, we're actually able to solve for the x value here. So solving for the x is equal to the square root of y times a squared divided by h. So let's go ahead and plug it in for the y bar here. So we have the integral from 0 to h, since we're doing it with respect to the y-axis here. The y bar is equal to y times dA, in this case is x dy. But of course we solved for the x with respect to the y here, and we could just plug it in afterwards. Then the denominator is the integral from 0 to h dA x dy, and of course we just plug in for x to further simplify this. So we're actually able to remove the constants here, which is a divided by square root of h here, and we see for both the numerator and the denominator we have the same, so these constants actually cancel out, and we have the integral of y to the power of 3/2 dy and the integral y to the power of 1/2. So let's go ahead and solve. So we get 2/5 times y to the 5/2 from 0 to h, and we have 2/3 times y to the 3/2 from 0 to h. So let's solve. And we finally have 3/5 h, and so this is our y bar. So now we have the x bar and the y bar, so now we're able to actually locate where the centroid of this area is. And this is how you solve for the centroids of areas. And it's the same if we're talking about cross section of a beam, then you would go about it the same way by using the formulas that were shown in the beginning. So it's definitely very useful to know, as well as because you have real world applications when it comes to doing your analysis on certain systems. You should be able to determine the center of gravity when it comes to certain objects. So you could apply the external forces or the weight of that object, as well as they'll help you do your calculations for any other kinds of analysis. So this is how you solve for the centroids of an area.